Hi. So as a fun game, count how many times I say NVMe during the course of this presentation. So I'm here today, obviously, to talk about NVMe Over Fabrics. NVMe was released as a specification over 3 years ago to standardize the interface to PCIe attached non-volatile memory. NVMe Over Fabrics is a mechanism to scale NVMe beyond PCIe to fabric attached devices. So I want to talk about a high-level overview of the NVMe Over Fabrics architecture, talk about some of the interactions to explain how a host would interact with a remote NVMe device. This is a really timely conversation because the NVMe Over Fabrics specification is going to be released end of May, and the NVMe Over Fabrics host software stack and the target reference drivers will be released very soon after that. So quickly going to go into the NVMe Express organization, and just one quick slide to talk about what it is. Then kind of lay out the case for NVMe in the data center and scaling beyond PCIe. Then a few slides on architecture and implementation of, as I said, the host and the targets and how they interact. And then finalize with some standardization and enabling to explain what's going to be available and when it'll be available. So the NVMe Express organization is a large standards body. It's 80 plus companies. I was actually just told today that it's over 90 companies now. It seems to grow quite fast. There are three main work groups. There's the technical work group for doing the specifications, and then there's the driver work group, which is working through the Linux drivers and the fabric transports that will be released. And then there's the marketing for NVMe awareness and evangelism. And the NVMe Express org website is large and extensive and contains lots and lots of extra information. And in fact, there's been a number of videos online that talk more about what I'm going to talk about today. So the logos on the side, these are a small percentage of the actual companies that belong to the NVMe consortium. These are mentioned because these have been the primary contributors to the driver development, and the ones with the boxes around them are the steering committee members and that sort of thing. So the evolution of NVMe in the data center. This is really kind of a mom and apple pie slide. In the method today for accessing fast storage in the data center is NVMe. NVMe has solved the way of scaling out non-volatile memory in a system. However, it has, as I think it's mentioned a couple of times this week, limitations of how many devices can be accessed in a system. Data centers are increasingly requiring larger amounts of devices to access, high availability, failover, data sharing, capacity, what have you. Traditionally, this has been solved with SCSI transport, iSCSI, ICER, what have you. However, they do add translations and protocol on top, which really limits the benefits of NVMe. In addition, new non-volatile memory technologies are coming out, which are incredibly faster than NVMe, and adding translations on top of those, ICER, what have you, really limits their benefits, really limits the effectiveness of these new technologies. So enter NVMe Over Fabric, which really is a way of scaling NVMe beyond the local system without translating and adding that sort of overhead, and provides a really low latency, high speed method of scaling NVMe onto fabric attached devices at nearly local in the box speeds. So let's see if we can get through some architecture. So the goals of NVMe Over Fabrics, we wanted to share the same base architecture and NVMe host software as NVMe over PCIe. In addition, we wanted to be able to support lots of fabrics. We wanted to be able to add fabrics as fabric technologies improve or get added. We wanted to be able to, when fabric resources become available in a system or get taken away from a system, we wanted to be able to access these fabrics. So this diagram really is just showing the NVMe host software, which is common as we're treating PCIe as just another fabric. It's a local fabric. And the same interface is used for data center fabrics. And again, these are lightweight, pluggable fabrics which can be added. The software is going to be released with the RDMA agnostic transport. This will work, and we've tested over InfiniBand, iWarp, Rocky. In addition, I know the fiber channel folks are developing a fiber channel NVMe Over Fabrics transport. Now, these are pretty easy to develop. The binding specification in the NVMe Over Fabrics, it's like 6 pages long. It's not that hard to develop a new transport. So to continue, the vast majority of NVMe architecture is leveraged as is for fabrics. I mean, we use the same host interface, some commands, same controllers, namespaces, that sort of thing. And we actually were successful. 90% of the NVMe Over Fabrics code is shared with NVMe Over Fabrics, or I'm sorry, NVMe Over PCIe. The primary differences are really laid out here. There's identification and discovery. Shouldn't get too far from the mic, sorry. There's identification and discovery, which locally, that's, you're probing your bus enumeration, that sort of thing. For fabrics, we use an NVMe qualified name to identify resources, and discovery and connection commands are used to find out what resources that you have, and I'll get to that in the next slide, and how to connect to them, and I'll get to that in the next slide after that. For queuing, obviously, PCIe is memory-based. For fabrics, these are message-bases. These are actually through defined capsules, we call them, that are common between all fabric types. For bulk data, PCI Express supports physical region pages and scatter-gather lists. For NVMe Over Fabrics, these are scatter-gather lists with added keys for the transports that can use them and want to use them. So I talked about capsules. So there's nothing magic here. All a fabric capsule is, of course, a well-defined message that sends standard NVMe commands across the fabric to the remote resource. You can include data in the capsule, or it can be sent bulk by the fabric-specific mechanism. RDMA reads and writes in the case of, say, the RDMA transport. And responses are just the same. These are standardized NVMe responses, which are encapsulated, maybe some data's in there, and sent back. So how does an NVMe host discover what resources it has been assigned and what resources it can access? So we're utilizing a discovery service, and this is not an incredibly new concept. This is a small service which could exist standalone on another server, or it can be on one of the remote targets. And a host is told where its discovery server is. This could be through a configuration or through something more sophisticated, DHCP, whatever you'd like. And an NVMe host will establish an ephemeral, short-lived connection to a discovery server. It will then identify itself and request information about its resources. It will get back log pages, a series of log pages, each consisting of an NVMe target subsystem it has access to, what fabric that target uses, the address type, IPv4, IPv6, what have you, that particular target uses, and the address. And if a target uses more than one fabric, if it's capable of being accessed by more than one fabric for failover, high availability, then it will get a log page for each of those fabrics supported on that given target. After which the host will simply shut down the connection to the discovery server and start establishing connections to each of its assigned resources. So the next goes into a little more detail. It's kind of a eye chart, sorry. So an NVMe association between a host and a given subsystem, controller, sorry, consists of an administrative queue and some number of IO queues. And when an NVMe host has established the NVMe administrative queue and all of the NVMe IO queues to that remote controller, after all that's done, then the association has been created, and the host can start using the remote NVMe resource as if it was a local NVMe drive. It shows up under /dev/NVMe, whatever, in the case of Linux. And so this is just simply showing how the host will use the fabric transport specific connection mechanism to establish for each queue that connection, and then send the connection commands. And if authentication is required, it can send the authentication tokens and authenticate itself. And then that
that queue has been created. And then once all the queues are created, then, as I said, the host can then use that NVMe controller. So this is sort of a, busy slide to show a transaction. So the operating system would send down a request. This could be an administrative or a bulk data request, read, write, what have you, to the NVMe Host software driver. That request could be encapsulated, sent across the fabric to the NVMe subsystem, which will then either, if it needs to get some data, it will grab the data and it will send that request onto the PCI, the real PCI NVMe controller. I want to point out that the NVMe subsystem is very lightweight, very simple. It is essentially a bridge between a fabric and a PCI NVMe controller. This could be instantiated as a piece of software on a server. It could also be instantiated as a piece of hardware, an embedded controller of some sort. So a couple of slides on the NVMe host and the target. So this is kind of a high-level architectural description of the host. What it consists of is the common NVMe core software, which is used by all the fabric types and PCIe as a transport. And it consists of a fabric library which understands the common NVMe capsules which need to be used to send commands over the fabric. And then again, these individual fabrics transports, the PCI transport, RDMA transport, fiber channel transport, whatever you'd like. They're small, they're lightweight, they're easy to develop. And they retain the efficiency of PCIe NVMe across fabrics. There's very low amounts of added latency, and we'll talk very briefly about that in a couple of slides. So the target. So I want to make it clear, the NVMe Over Fabrics specification does not tell you how to define a target. That is implementer specific. There is a reference implementation which is going to be provided, but one could design their own target essentially how they want, by following the rules. It really is, there's the fabric transport, and we're providing the RDMA transport. The NVMe target core is essentially a logical representation of NVMe controllers, subsystems, and namespaces. It simply sits between the fabric and the real PCI NVMe device. It's responsible for discovery and configuration, fabric commands, data, sending and receiving, that sort of thing. This is something that, as I said, we provide, but one would develop on their own. And there's a lot of room for value add here, or doing it in ways that would show off your particular hardware. So, coming to the end here, the Linux host and target kernel drivers are operational. They have been tested with local host PCIe. They've been tested with accessing over InfiniBand, Rocky, and iWarp to remote targets. And we've tested them with 3 different target implementations. So it's rather a large matrix of compatibility here, but they are working. And right now, the driver team are mainly making sure that we're fully spec compliant and that where they're being performance tuned essentially. Now, as I said, there's such a large matrix that full performance tests have not been done, and I haven't done them and I haven't seen them. I do know that a long time ago we were showing less than 10 microseconds of added latency round trip per NVMe transaction. So I don't know what the state of it is today. So NVMe Over Fabrics specification, it's complete. It's in the RFC stage essentially. It's being voted on, and it should be available end of May. The host and target drivers will be available in the upstream Linux kernel under drivers NVMe, host, or target. Sometime, probably 4.8, probably roughly when the specification is released, maybe soon after. And I said we support local PCIe fabric. We support a fabric agnostic kernel verbs transport, and fiber channel probably will be in there. And then I do know that other transports are under evaluation. I mean, I know it's been mentioned a couple times about Kfabric as another transport. And so really the call to action here is when the specification has been made public on the NVMe.org website, and when the drivers are available, please get them, please look at them, please test them in your environment on your hardware, and see how it works. And of course, disclaimer slide, yay. And thank you.
What's the difference between the local PCIe and the PCI fabric as far as NVMe is concerned?
I'm sorry, I don't understand the question.
You mentioned that in the NVMe fabric you can have PCIe as an interface as well.
Right.
So what's the difference between local PCIe, NVMe versus fabric?
Right, good. So effectively, we want to have the same host interface so you can access your own PCIe devices on your own system. And you'd like to be able to access them remotely over Fabric. So the real difference is PCIe is treated as another fabric, and those requests are just routed through to that transport. So the difference is that requests are either sent directly to the device, or requests are sent as messages in capsules and then sent over to the other side. Does that make sense?
Maybe, I don't know. I'm not very clear, but yeah.
Okay, well, I'll be here all week, so feel free to come talk, try the deal. Any other questions?